Hey, this is Brock Lemires, and in this video I'm going to talk about logic operators in C and also how to use them to perform what we call bit masking. All right, so C provides a set of logic operators at the bitwise level. And what that means is that the operations are conducted per bit within a word. Okay, and so the operators that it gives you are not, which means invert, 0 becomes 1, 1 becomes 0, an AND operation, OR operation, XOR operation, rotate left, rotate right. And when you do this, if you think about an example where you had an 8-bit input and an 8-bit input, if you performed an AND operation, it would do an AND on every bit position. So for this position right here, position 0, it would take this 0 and it with this 0, and the result would be right here. Okay, in bit position 0. Same thing, if you came over here, it would be 1, and with 1 gives a 1. So it's performed on a bitwise level. That's different than like taking the whole word itself and saying, is it equal to 0? And if so, every AND operation will result in a 0. It's per bit, okay? All right, so here's the syntax for using these. The complement operator is a tilde. And what you do is you basically just say var equals tilde var, and every 1 will become a 0, zeros will become a 1. The OR operator is a pipe, and you can do var equals var pipe a number, okay? Or you can use a shorthand. So if you're ever going to operate on just yourself, C provides a shorthand where you basically put the operator in front of an equal sign, and then you just give it the other argument. Okay, so this as an example, like if you were going to say C equals A ORed with B, that has two different input arguments and a different output. So you would have to say A ORed with B, all right? But if you did something like this where you're going to take var and you're going to have it be one of the input arguments, then you can use this shorthand. And you'll see why that's important when we do bit masking here in a couple slides. Okay. So anyway, these two are identical. It's just this is the shorthand. And you use the shorthand like crazy when you do embedded programming because you're constantly configuring bits within registers. Okay. And then the AND operation is an ampersand. These are all single symbols. Okay, we'll have double symbols here when we get to decisions, but for now, these are actual operators and they're single symbols. And same thing, you'd go var and with another input argument, or it also has a shorthand where you can put the ampersand before equals if you're operating on the destination argument with another input variable. XOR is the caret. This performs an exclusive OR. The shorthand is caret equals if the destination variable is also one of the input variables. Then you have rotate left and rotate right. So you basically have less than, and greater than. And the argument for this has a number of rotates. Okay, so if I wanted to rotate var1 or var to the left by 1, you would put a 1 after here, and this would do it 3 times. And this becomes really interesting because you can take all the bits and you just move them to the left, tick, 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 so they kind of shift over, and then you fill the vacant spots with zeros. Okay, same way here. Fill the vacant spots with zeros. Okay, all right, there is a priority here. So we have not gone through all the arguments, all the operators, but as we do, we kind of look at their priority relative to the other ones. So we've already covered math, right? So we've covered the multiply, divide, and the remainder. And we saw how that was higher priority than the add and subtract. Well, it turns out these unary logic operators are higher priority than these guys. Okay. So we're building up this huge table of operators and their priorities or their precedence. Okay, now, the vast majority of the time when you're using logic operators, you're doing this thing called bit masking. Now, a bit mask is where you take an input argument and you operate it on it with a constant binary mask or a binary operator. So, not operator. Mask. Okay, so it's a constant. And we do that because you'll see that depending on the logic operator, you can clear set, or toggle specific bits in the first input argument depending on the zeros and ones configured in the second argument, or what we call the mask. And so as we go through these logic operators, you'll see that depending on whether it's a 1 or a 0 will tell whether you're going to clear, set, or toggle, or if you're just going to leave it alone. So let's go through the logic operators. Here is an AND gate. This is your standard symbol for an AND gate, and here's the truth table. Anytime you have 0, or let's go through it. 0 and 0 ANDed together gives a 0. 0 and 1 ANDed gives a 0. 1 and 0 ANDed together gives a 0. 1 and 1 ANDed gives a 1. So that's the AND operation. If you notice though, look, let's say that A is like, if we look at A being a 0 and a 0, what happens is that it doesn't matter whether B is a 0 or 1, the output's always a 0. So what you could say with this is that anytime you AND anything with a 0, the result will be a 0. This is how you clear a bit. What's great about this AND operation is that if you look at these two input rows, 1, 0 and 1, 1, if you AND anything with a 1, what happens is that the output is simply what the value of the other input was. So in this situation, B was a 0, the output was a 0. B was a 1, the output was a 1. This means ANDing anything with a 1 simply leaves the input alone. It doesn't have any effect. Now, this is cool because this gives us the ability to clear a bit. So consider this this input right here. I've got 1, 1, 1, 1, 0, 0, 0, 0. We call that the input argument. And the second argument is going to be the mask. So let's say we had a mask of 0, 0, 1, 1, 1, 1, 1, 1. What we do is we take advantage of the fact that anywhere I put a 0 in the mask, it's going to clear the bits. Anywhere I have a 1 in the mask, it will preserve the bits. So in this situation, if we start at the least significant bit, these 6 bits are 1s in the mask. That means it's just going to basically take the 6 bits of the input argument and just preserve them. So it was 1, 1, 0, 0, 0, 0. Those are right down here in the output. 1, 1, 0, 0, 0, 0. It had no effect on them. However, look at what happens when the mask is a 0 in the AND operation. It will clear these bits. So they both happen to be 1s. No longer. They're now 0s. So we use an AND operation to clear bits by putting a 0 in the mask. Okay. You can also test with this operation. And what a test is where you say, I want to know if a particular bit was a 1 or not. Okay. So consider this example. Let's say I had an input of 0, 0, 0, 1, 0, 0, 0, 0. And I asked the question, is bit position 5, or let me count that, 0, 1, 2, 3, 4. Is bit position 4 a 1 or a 0? So you could put a mask of 0, 0, 0, 1, 0, 0, 0, 0. And in this situation, you'd say, I want to test whether this bit position is a 1 by performing an AND. And what happens is that if this bit position was a 1, the result of ANDing it with the mask will result in a 1 in that bit position. But more importantly, the whole word of the result will not be 0. Okay. And so you can say, is this value greater than 0? And if it is, that bit position was indeed true or a 1. Now, if this position right here was a 0, like over here, you could say, in this test case, you say, is bit 7 a 1 or a 0? You clear every bit in the other bit positions because you don't care about them. And then in this situation, the input argument was, or the input bit value was a 0. You add a 0 and a 1, it actually ends up as a 0. This entire word is a 0. So you could say, is the word equal to 0? So the question was, is bit 7 of the input equal to a 1 or a 0? You look at the output based upon the ANDing with this mask and you say, it was equal to 0. So the answer was no. So these are two questions you can ask, and you can use the AND operation to do that. So AND is used for two different types of questions. One or two tasks. One is clear the bit or clear bits that you want using a mask, or testing whether a bit position or positions is equal to a 1 or a 0. So it's very useful. How about a set? So a set is where you use an OR operator. So let's consider the OR operator. Here's a standard OR. You have A and B OR together. And what happens is for all the input combinations, the output is 0, 1, 1, 1. All right. What that means is if you look at the input A, if it's a 0 and you look at B, if B's a 0, output's a 0. If B's a 1, the output's a 1. Then you come down here and you're like, okay, now A is going to be a 1. Notice that if it's a 0 on B, the output's a 1. If B is a 1, the output's 1. So essentially, anytime you put a 1 on the input, the output's going to be a 1, no matter what. If you put a 0, then the output will be whatever the other input is. So here's the summary of this. ORing anything with a 0 has no impact on the input in this situation being B. And ORing anything with a 1 will result in the output always being a 1. So that is how you set a bit. So here's an example of it. Let's say that I had a input argument of 1 1 0 0 0 0 0 1, and I had a mask that was 0 0 0 1 1 1 1 1. I OR these together. Any of the positions in the mask that are 0 will preserve the bits. So these 3 bits came straight down. 1 1 0 came straight down into the output. However, all these bits, these lower 5, they are going to be set because anything ORed with a 1 is a 1. So we set all those bits. So that is how we use an OR operation to set. Finally, we have a toggle. Toggle is where you can basically complement an individual bit by using an XOR operator. Sorry. Okay, so same thing. Here's the output of a true tuple for an XOR, 0, 1, 1, 0. Notice that if you XOR anything, we're looking at A now, with a 0, B passes to the output. So if B's a 0, the output's a 0, B's a 1, output's a 1. That means ORing something or XORing something with a 0 preserves the bit. But if you XOR it with a 1, look at what happens. If B's a 0, the output's a 1. If B's a 1, output's a 0. It toggles it. So we can say that XORing anything with a 0 has no impact. XORing anything with a 1 will actually complement the value. And so here's your example again. If I have an XOR where I have 1, 1, 1, 1 in the mask, 0, 0, 0, 0 in the mask, the bottom 4 bits will preserve, the top bits will toggle. So in this example, if you take the bottom 4 bits of the input argument, 0, 1, 0, 1, they're preserved, 0, 1, 0, 1. And then let's look at this one, 0, 1, 0, 1. You're going to toggle them to 1, 0, 1, 0. All right, let's do it. Okay, so here's what I'm going to do. I'm logged into the Linux server, and I'm going to go ahead and change into, let's see where I'm at here. Okay, so I'm going to change into my mod 04 code along. And what we're going to do is make that a little bit bigger. And then what I'm going to do is take a look what's in here, and everything's good. So I'm going to create a new file called logic testing using Vim. So I'm going to say vim logic testing.c, and it's wrapping the line. So let's just go a little bit bigger than that. Okay, here we are. So now let's code in here. So I'm going to let's put in our comment header. So I'm going to go ahead and say playing with logic operations. And we'll go ahead and close that up. And now let's bring in the standard IO header file so that we can use printf. So I go pound include and then standard io.h. And then I close that. Now let's do the shell of our main function. So I go int main void open curly, go all the way to the end, return 0, and then close curly. And now let's save this thing. So I hit escape to go into normal mode. I hit colon to go into command mode. I do W as the command, that writes it. All right, come up here. And what I'm going to do is now I want to create a binary value. And I am going to take advantage of the fact that our compiler allows us to display information in binary using the syntax 0b, okay? 0b means binary. If I do an unsigned car, remember, car is an 8-bit value. Unsigned means don't allow any of the fields to be treated as negative. And if I do this syntax right here, I will actually get a binary value. And it's not supported. 0b is not supported on all compilers, but it is on our Linux server. So this is awesome. So watch what I do here. Unsigned car. And that's the data type. I go var1, and I'm going to go equal. In binary, I'm going to go 0, 1, 1, 1, 0, 0, 0, 0. And now I've done that. And now what's really cool about our compiler is that we can actually go printf, and then we can go var1, equals, and then I can actually do this. %B is the format specifier. Okay. But I come in here and what I want to do is I want to go 08. That specifies the width of the binary number. It's going to print it in binary. It's going to make sure it's 8 bits. And to make it 8 bits, it's going to fill with a 0. Okay. So for example, if I printed this without that 08, I would get 1110000. But I want it to always be 8 bits so that it's aligned. And let me just show you that. So that's pretty awesome. That's like a huge deal. So I'm going to take this thing and I'm going to copy and paste that. I did YYP. Okay. And I'm going to do this. Okay. So let's see it with the formatting and without this formatting. Okay. All right. So it's complaining like crazy. It's like, hey, got to remember your commas. Got your free throws here. All right. So we got that. Let's go down to our other shell here. And first of all, where are we? I'm in my home directory. So I'm going to change to my mod 04 directory and take a look at what's in here. Oh boy. Let's do an ls instead. Let me bring this up so you can see it just a little bit better. So let me clear that crud out. ls. Okay. GCC, and I'm going to do logic testing. That was horrible. ls, look at what I did. I didn't give it a dash o, so it compiled into a.out. Let me get rid of that right away. Okay, let's try that again. GCC logic testing. Let me bring this all the way over. Okay, it's GCC logic testing and then dash o, and then I'm going to send it to logic testing with no extension. Okay, ls. There it is. Now let's run logic testing. Let's see what I get. Notice that in the first case, okay, so I'm kind of back to, let me clear that again. This is a mess. Okay, in the first case, it used the %08B. 08 was the width. Give me 8 bits and pad it with zeros if you need. That gave me the perfect 8 bits. But if you don't do that, what it does is it doesn't show you any leading zeros. So we want to see the leading zeros because we're kind of playing around with bit masking. So that's where that came from. Okay, awesome. That guy's out of our life. All right, now let's do this. Let's go ahead and just try them all. Because this is awesome. So let's just do this one by one. I'm going to do every single one of these. So let's do this. I'm going to go, let's do complement. Okay, so I'm going to do this. Bar1 is going to equal tilde bar1. Now watch what I'm going to do. I'm going to come in here and I want to print bar1. Okay. So I want to do this. I'm going to come up. I'm just going to do this. I'm going to copy that, paste it, and I'm going to say this bar. I'm going to say, I want to do something cool like a complement, and then what I'm trying to do is line up these things so that they look really good. So let me do this. I'm gonna put some spaces in here. Let's see if this lines up. I want the bits to be obvious that they're lined up. So let me do this here. Compile this up, and then let's run that. So they're lined up. Okay, so you see how, let me clear that and show you again. So I just space those over so it's easy to see that 0, 1, 1, 1, 0, 0, 0, 0 was complemented and all the bits changed. Okay, yes. All right, now check this out. Now let's do this. I want to clear bit 0 using AND. Okay, now we're going to use an AND mask. Okay, so here's what I'm going to do. I'm going to come right here and watch how I do this. I'm going to go bar1, and I'm going to use the shorthand for an AND operation by putting AND %equal. And now I'm going to provide a mask. Okay, so remember, I'm going to enter 0B for binary, and I'm going to say anywhere I put a 1 in the AND mask will preserve the bits. Anywhere I put a 0 will clear it. So if I go 1, 2, 3, 4, 5, 6, 7, 0, that is going to clear bit position 0. Okay, so now I'm going to come up here and I'm going to copy this line by doing YY, and then I go P, and then here I'm going to do this. I'm going to say clear bit 0, and we'll line up the equal signs, and now I can test this. So here I go. I'm gonna come down here, GCC it. Okay, logic test. Oh, buddy, look, baby, look at this. Look at how bit position 0 was cleared. I did it with an AND operation. Okay, let me pull that over there. There's a lot of stuff going on. So let me cover up the output of the slide because it's a little confusing. Okay, let's do a set. Okay, so let's set bit 5. So I'm gonna go set bit 5 using OR. Okay, so I'm gonna do this. I'm gonna go var1, and I'm going to use the OR operator, which is a pipe equal. That's the shorthand when var1 is part of the input arguments. And now I'm gonna use a mask 0b. And remember, with an OR, anywhere I want to preserve the value, I put a 0. Anywhere I want to set, I put a 1. That's different from when you use the AND. So you have to keep track of what are you trying to do? Are you trying to clear or are you trying to set? And depending on that, you use the particular logic operator, and then you use the mask differently. So in this situation, I want to preserve bits 7 and 6, but I want to set bit 5, and then I want to preserve 4, 3, 2, 1, 0. Okay, I'm going to copy this line right here, YY, and then I go P, or I hit P. I'm going to do set bit 5, and then let's try to line up our spaces so that we can see it. All right, now here we go. Come down here. Doop, doop, doop. All right, let's clear that baby up and then run it. Oh, look at this. Bit 5, which was this one right here, it got set. So I did it. Notice that this was 1, 0, 0, 0. Now it's 1, 0, 1, 0. I set that bit using an OR. All right, let's toggle. Okay, so now I'm going to do this. I'm going to go toggle, and let's do bit 6 using XOR. Okay, so I'm going to do this. I'm going to say var1, and I'm going to use the shorthand. I'm going to go caret equals for exclusive OR with a bit mask. And remember, when I toggle with an XOR, anywhere I put a 0 in the mask, the bits will be preserved. Anywhere I put a 1, it will toggle it. So in this situation, I want to preserve bit 7, toggle bit 6, and then preserve bits 5, 4, 3, 2, 1. And then let's print it. So I'm going to come up here, I'll go YY, come down here, hit the P button, and then I'll come right here and I'll do toggle bit 6, line up my little equal signs, and I should be good to go. So now let's come down here. I'm going to go GCC, and then I go logic testing. Let me clear that and move it up a little bit. Okay, look at it. Bit 6, where was it here? Toggle bit 6. Toggle bit 6. So I got toggle bit 6. So I had I didn't have enough zeros, did I? So 7, 6, 5, 4, 3, 2, 1. I forgot a 0 here. 0. Okay, so that math, it was toggling bit 5. I don't want to toggle bit 5. I want to toggle bit 6, like I said. So let's try that again. Let's hold GCC, logic testing. Here it is. Let's clear that, move it up just a tiny bit. Now, bit 6 has been toggled from a 0 to a 1. Okay, we did it. All right, let's take a look finally at the rotate really quick. So let's do rotate left 2 times, and we'll see how that works. So we'll come in here and we'll go var1 equals var1, and then I'm going to go left shift or left rotate 2 times. Let me grab this right here. I'll do YY, and I'll hit P for paste or put. And then I'll do this. I'm going to say rotate left 2. And let's get those lined up. Whoops. And we'll go right there. Oh boy. All right, let's see if that worked. So I'll come down here and I'll go ahead and run that GCC, and then boop. Oh, look at that. So look at what happened here. Let me clear that and show it to you again. Look at what happened. I took the whole field that was sitting right here and I shifted it left 2 times, and I filled in zeros. So the 2 locations that didn't have anything in them on the right got filled with zeros. So instead of having, I'm going to count from the right now. 0, 1, 1, 1. That 0, 1, 1, 1 is here. 0, 1, 1, 1. So everything shifted to the left 2 times. All right, last one. So let's do a rotate right. Let's do 3 times. Okay, so I'm going to do var1, and I'm going to say var1, rotate to the right 3 times. Not L times. 3 times. I know. Here we go. Here, var1. Come on. This video's too long. YY, P, come over here. rotate. I'm not sure why I deleted that. Rotate right 3. And the equal won't be lined up, so let's do it like that. Okay. So let's come down here. I'm going to go GCC, run it. Oh, look at it. Look at it. So now I rotated the whole thing 3 times and it filled the most significant padded bits with 3 zeros. Okay, we have done every single one of those. So that's the logic operators in C. They're bitwise, and we use them predominantly in microcontrollers and embedded computing to do bit mask operations, specifically set, clear, toggle. All right, nice work.